this episode, we're going to talk about SGM cost function color constraint. SGM stands for semi-global matching. Is one of the stereo vision algorithms. So the agenda of this episode is we're going to talk about first is disparity, the second is census transform, and third was matching cost function. It means the color constraint term. Okay, so the cost function, the overall cost function for semi-global method is kind of like this, but this actually is a modified version. The original semi-global matching is not feasible to implement on FPGA, so we have to change this into census transform. So we will talk about this right away. So before we and when you look at this cost function, don't be scared. It actually can be separated into two parts. First part is a color constraint term, and that is today we're going to talk about. The second one is a spatial constraint term, and we will talk about in the next episode. Before we explain this, we need to understand disparity and census transform or matching cost function. What is a disparity? So for any point in the 3 dimension, they've got a projection into two symbols of the stereo vision. So by the way, this is a stereo vision prototype setup. There's two cameras. This is my very first version, and using two USB camera and using the glue to stick them together. Of course, we need to, before we do the we have to do the calibration using the chessboard, and then we can get the distortion, translation, rotation, and coefficients. And remember that this left and right image may not be rectified like this. So the original image may look like this. Left and right may have the rotation and translation. So we need to do rectification using these coefficients. We journey this before the production. In production stage, we all have to do this calibration for each stereo vision camera. Okay, so the purpose of the calibration is to get the distortion and translation, rotation, and TOF, this kind of a lot of parameters. Then we can fit into this rectification module, and then we can rectify this image. The purpose of rectification is to set this up epipolar line in the same horizontal. That means that when we're trying to search the corresponding points in the right image, we only have to search in the same line, horizontal line, and we don't have to search in the whole image in the right image, whole pixels in the right image. That will be horrible because the computation will be very large. Okay, so that's a good thing about rectification. You can narrow down this search on just one line instead of whole image. Okay, so the disparity is calculated by this disparity. It's this in the left image projection. This point is CL, RL, C means column and row. Okay, then also in the right image also, and this is origin. This is origin. So this origin points. Then the disparity will become CL minus CR. CL is larger one, minus CR. And that is the disparity in terms of pixels, the unit pixel. Of course, sometimes we have to set the maximum value for disparity. For instance, here the empirical value is 64. It actually can satisfy a lot of using scenario, but also you can set it to 180 or 256. That depends on your resource and how much resource you're going to pay for that. The higher this value, that means the more resource you're going to use in FPGA, especially the background and the lookup tables. It's quite expensive. So 64 is a reasonable value. So what if you increase this number, this Dmax number? Remember that when you increase number, okay, so let me talk about this distance. The distance, how do you get the distance, z distance this is the formula. So it's inversely proportional to d. That means that this is the closest point you can observe with this stereo vision. This is the closest distance, and this is the farthest distance you can observe when d equals to 1, disparity equals to 1. When d equals to 1, this is the farthest sorry, my English is so poor. Okay, you get the idea. This is nearest point. So if you increase this Dmax, that means that you can observe near distance. Okay, so that really depends on your usage scenario. Sometimes maybe you want to observe very near distance object. Of course, also it's because remember that as d is quantized, it becomes 1, 2, 3. So the distance z is actually quantized. This is and then quantized is a quantized distance. Okay, so the further the error rate, the error is much larger, because you cannot for this stereo vision, okay, you cannot tell which distance here. Maybe you will say, oh, okay, you belong to this. So the error rate is much larger the farther away. When it goes near to near, and the error rate becomes close and close, small and small. So in the optimal observation range, you can get to the error into level of 1 millimeter or several millimeters, just in this level. Okay, so that's how you set your Dmax. The objective of this FPGA code is to find the corresponding points between left image and right image. For instance, I have to, for each image in the left, how do I know the corresponding point in the right image? So this is a key job of stereo vision. You might think it's easy. It's not easy. It's very complicated. And stereo vision algorithm has been exist for decades, but not much of them has been to implement on FPGA and to make it into products, because the computation job is very intensive. It's really intensive. Okay. So and that's our job, today's job, to how to accelerate this impossible mission for on FPGA to make it into a reasonable product, which balance the cost and the performance. Okay, after you found this corresponding points, then the second step is quite easy, to calculate the disparity for each image pixel. Okay, so this is a disparity map. For instance, maybe this is a disparity corresponding to this left image. For each image pixel, you have the disparity value attached to it. That means the 3D information x, y, z. Okay, so disparity actually is grayscale value. The larger, the more near, and this is the colored version. It's quite easy. It actually is to interpret the distance in terms of color. It's better for eyes to perceive. Okay, so the colder image, the colder color means the dark blue is far away. The hotter color means red. It means that it's closer, more closer. Okay, so this is the disparity. From the disparity 3D coordinates, it's quite easy. This is the formula for for the rest of x, y, I didn't list it. It's quite easy. It's a similar one. And okay, so as I mentioned, this second step is quite easy. Most of the algorithms that exist for decades, where people are trying to find a way to find the corresponding point. You find this very tiny step, but it takes people to spend decades to search for this. Because you may, for human eyes, maybe this color block, maybe corresponding to this color block, but for the computer, how do they understand that? Because there's a lot of mismatchings. Okay, we'll explain that later. Okay, so the methods to find the corresponding points, this is the key job here we're talking about. It's barely impossible directly using pixel values, RGB or grayscale, which is a standalone color information. Okay, why this is fatal? Because left and right CMOS exposure conditions hardly be the same, so pixel value can hardly be the same. So maybe here is 250. Here, this same corresponding point maybe 246. Okay, there always some discrepancy between two left and right image because the exposure conditions is different. So it's very hard to find it's barely impossible using pixel value. Okay, so then people come up with some other methods. Actually, HOG is not applied for stereo vision. It's used to find feature points in the consecutive image. For instance, we want how can I find the corresponding point between this image and that image? This image and that image may be taken in different time, not like a stereo vision. Okay, so this is the idea to find the corresponding point between two images is to encode the color information. Since the standalone color information is not feasible, it's not enough. Information is not enough. Then how can we? And then we may ask ourselves, can we encode the corresponding color information into this in this pixel? It means that we have a color, then maybe there is a gradient. Gradient means a color change between the one image. Okay, between one image, between the pixel between these neighboring pixels, there's a changing pattern, and then we can embedded this into as a feature. The feature expresses the relationship between its color information, changing relationship with its neighboring pixels. How do they do that? We do the grading. For instance, here we have 8 directions: horizontal, left, and top right. So we do this gradient calculation, and then in 8 directions. Okay, so and then we choose the biggest one, the biggest value. For instance, here 118, as it is starting index 0. So here we have a 0 to 7. Okay, so then we can stretch this value into this 8 bits, and then we become to have one-dimensional vector as its feature, and this vector says its relationship, this pixel's relationship with its neighbors, 8 neighbors. Okay, so because and it's kind of unique, not very unique, but it kind of means that it would that it makes it standing out from the other. If you were using this vector, it's very, then you can cross out. You can remove a lot of other non-relating pixels. Maybe only a few few points in the right image can match in this. Can have the same vector. Okay, so but I hope you got this idea. My English is not so good. Okay, and the pros and cons for this HOD is that the explosion conditions won't affect the color gradient, and also its shift and rotation and scale invariant. Actually, if you learn the open computer vision, this is again it's a shift operator for finding these corresponding points in different images. Okay. The cons is that it's computationally extensive. Okay. The solution to this is using census transform feature, right? Because we don't need that complicated for stereo vision, because in stereo vision we already have rectified first. We already have rectified it. We already know the scale. We are in a sense scale, and also in a horizontal position. So we can simplify the features. We don't need that complicated feature method operator. So we can use the binary pattern features. It means that for the center point, I only have to find its pixel relationship with its neighbors by saying if the value is larger than the center, then we'll put 1 here. If it's smaller, and put 0. Okay, so we get the 1 0 1 0 kind of this binary pattern, and we always starting from the fixed position. For instance, here we always start from x0 0. Of course, you can start from here as well, and you just have to get the persistent to that order. So otherwise you cannot match them. So if you started from here, then we can stretch it to get a one-dimensional vector. And here, remember, notice that it's 1 0 1 0, and here it's maybe it's a 8-bit or 16-bit long. So it's a huge vector, huge compared to is a huge vector that takes up a lot of memory. It's a huge. Maybe this one is 8 bits long or 16 bits. Here just 1 bit. Then will become so much easier for processing. Okay, so for the operator here is 3x3 sensor transform kernel. After transform, you also get 8 bits. This is for instance, is maybe the 8 bits. Also becomes 8 bit. Sorry. No. It becomes 8 bit. Okay, here, this is 8 bit. Now let's make a general one. This one, the memory layout of a sensor transform. In this project, I use kernel size is 7x9 because you want to embed. You don't want to just compare just to its direct neighbor. How do I make this more unique, more special, standing out from the others? More this feature more unique. Sorry, how to more special. Okay, more special. Okay, so then we can expand this the comparison region, this is kernel size, to be 7x9, and then we compare it to more neighbors, more neighbors. Okay, then we have this depth after the transformation. The depth will be 63. 7x9. 7x9. Okay, so this memory layout of the sensor transformation will be like this. Okay, from 8 bit to grayscale to the 63 bits. Okay, now let's talk about how to matching cost function. The matching cost function's color constraint term. For this formula, we have to understand that P means each pixel in one image. If you want to minimize the whole E, and we actually only have to minimize for each pixel, then we can approximately achieve the global minimization. So this is what it means, what I just said. And now let's decompose this one, remove this one. How do we minimize each item? And we use the similarity distance of two vectors. This XO, if these two vectors are close to each other, means they are the same. Okay, means these two vectors are actually the same. XO. So that's that operator means. Now, since we know we're using SO, and for each pixel, we have the 63 bits vector, bit long vector that express its color feature with its neighboring pixels. For instance, we have the pixel P XL in the left image XL, and we are searching on this epipolar line, one send line, and we're looking left. In the right image, we're looking to the left, and for instance, we say okay, XR it is its minimum position. Then we have like a parabolic shape like this. It's easy to understand. I mean that it's when you're far away from this center, it's like the vector different, the feature different, feature information. The vector may be more different from this center. So far away, it should look like the champ. The champ looks like this. So this one, by matching 64 63 neighbors. You're here and searching one by one, exhausted and exhaustive searching to the left. Remember, we have disparity is maximum disparity is 64. So we have the 63 neighbors to search, exhaustive search. We can find the minimum one. If we print the value out, maybe we look like there's a champ. I equals to 1 to 63. Okay, first one. Okay. And di is xl times xl minus xr. Okay. Okay. This is the matching cost function. The cons of this matching cost function is that the color constraint item based on sensor transform feature map alone it's possible to find the corresponding pixel in the right image, but the drawback is the too many mismatching could happen because due to the repeated color pattern. Sometimes in a place you have repeated pattern color. Okay, so you will have multiple mismatching, multiple place to say, oh, I'm matching this. How do I know for the computer to tell that this is a representation? Because it's not human, they have the spatial feeling. Okay, so next step is we need more constraints. It should mimic human eyes. Can we add a spatial constraint to that? Okay, this is this is the next episode's it's all about. Okay, thank you so much for the time.